All right, so the whole thing about calculus is learning how to model real world situations. So we're beginning with the basic, easiest ones to eventually build you up to be able to model with calculus. So the classic calculus problem always starts with this. We have a piece of paper, 11 inches by 8 inches, almost standard. Instead of a 8.5 by 11, I made it 8. So if you cut out 1-inch squares on each of the corners and make a box, what will the volume be? So just think about you're cutting out these corners right here and you're folding this paper up to make a three-dimensional box. So this is what it would look like. You cut out these corners, you fold it up, and you get box. And as you can see here, every single time, what the calculus is going to do is we're going to look at making these corners different sizes, and you can see here how the volume is changing. All right, so let's look at this a little closer. If we started with these boxes being a cutout size of 1 inch, that means this is 1, all these are 1. That doesn't look like a 1, sorry. So the box volume, remember, volume is length times width times height. 9, 6, and 1, where'd 9, 6, and 1 come from? Remember, length times width times height. Well, the length wouldn't be 11 anymore because you took an inch off and an inch off, so now it's 9. Likewise, it wouldn't be 8 anymore because you took an inch off and an inch off, so it's 6, and the height is 1 because the inch represents the height. So this could be that cutout size of 1 inch. All right, when we multiply that all together, we found our volume to be 54. Great. Now, what if we made those boxes 2 inches? Well, then our length would be 7. 11 minus 4 is 7. 8 minus 4 is 4. We have a height of 2, and it's 56 inches. Hey, let's cut out a bigger number. Let's cut out 3-inch boxes, because look, our height's going up and up and up. We'll get maximum volume. So let's make this 3, 3, 3, 3, 3, 3. All right, cut out 3, and our volume is 30. All right, well, it's 11. Take away the 3 and the 3. 11 take away 6 is 5. 8 take away 3 and 3, so 8 take away 6 is 2. 3, 6, 30. Looks like there's more volume, but mathematically showed there wasn't. And what happens if I take away 4 inches? I get a volume of 0? Well, yeah, it makes sense. If these were 4, $11, 4, 4, 11 take away 4 is 11 take away 8 is 3. And then what would happen here? Well, you have 8, and you're taking away 4 inches from here, and then another 4 inches from there. You're being left with 0. So this is all well and good. What we want to see is, where is our maximum volume? Was it 56? Well, we can model it and get a clear picture and get a precise answer. So we want to take that information that we just had and we want to turn it into an equation. So the length times width times height, which is our 6th grade volume formula, is now going to be algebraically represented. The length is 11 minus 2x, because the paper started with 11 inches wide, and then we took the same amount off twice from each end. Likewise, the width started off with 8, and we took off 2 x's from each side, and then our volume was x. So if we rewrote this, it would be the function where we take the length of 11 minus 2x, multiply it by its width of 8 minus 2x, and finally by the height of x. We need to understand this is a cubic graph. All right, we should see that right away. X times x times x is x cubed. So we know when we graph it, it's going to look as such. And we know it's going to be one tail down first, followed by one tail up, because if we multiplied our x's out, negative 2x times negative 2x is positive 4x squared, times it by another x right there is 4x cubed. So we know our leading coefficient is positive, so this is indeed how our graph is going to look. What we're looking for is the relative maximum, because we want to find the most volume, the highest volume there is. What's the domain for the graph? Well, we found out back here that we can't take out a cut size of 4 because then that would give us 0. So there's obviously things that we can't use for that square. What's the range of the graph? Well, the range is the volume. We're looking for the highest volume. Hey, isn't that kind of like the relative maximum? Yeah. Well, what is the range for our specific piece of paper? That's really what the volume of max volume is. And what is our domain for our specific sheet of paper? So I kind of looped those all together. Let's get a visual of what this looks like. I'm going to come here to Desmos, and I'm going to type that picture in. 11 minus 2x, 8 minus 2x, and x. Wow, I can kind of see the cubic shape here, but I'm actually going to zoom out. Oops, zoom out. And I'm going to rearrange my settings so I get a nice picture of this. So I'm going to come here to my settings, and my x-axis, I want to go from 0, and it looks like, to 10. And I'm going to step by 1. That means I'm going to increase by 1. My y-axis, well, we looked up here, and when we press that point right there, 60 is my y value. So I want my highest y value to be at least 60. So I'm going to give it 75 because I like to see a little room. And I'm going to do my y-axis at negative 10. And I'm going to step by 5s. All right. And I'm going to, one other thing, I'm going to put this on projector mode. There we go. That's a big picture. That's a much better, that's a mo better picture. All right. So I am now, because it's Desmos, I'm going to highlight my maximum, my relative maxima, my relative minimum, and my zeros. And now let's take a picture of this. All right, so what is this picture telling us about this graph? Well, first of all, it's telling us this, that the maximum volume is approximately 60.01. That is the highest volume we can get out of this box. And you know when that highest volume is going to occur? When our cuts are 1.525 inches. So we saw over here that when we put 1.5 in, when we put 2 in, we got 56. So in between here, makes sense, is 60 approximately, right? We're going up at 1. We saw our answer was 54. At 2, we saw our answer was 56. So there's our relative maximum, 60. So we are looking for the relative maximums. That means our maximum volume is roughly 60.01. Now the domain of the graph goes from negative infinity to positive infinity. The range of the graph also goes from negative infinity to positive infinity. But we don't care about the whole graph. We only care about our piece of paper. So our piece of paper has a domain from 0 to 4. Our range is from 0 to 60.01. Now, some people may argue that 0 is really not the domain. 4 is not really in the domain, because when we put 4 in, we get a volume of 0. Well, guess what? A volume of 0 is an acceptable answer. It means the volume doesn't exist. It's a number, but we just wouldn't want to create a box with a volume of 0, but it is possible. So even though this graph goes on forever and ever, we're only concerned with this part in here. Because you couldn't put in cuts of 5. See, if you put in cuts of 5, you get negative volume. Because remember, our paper was 11 and 8. And if I take away a cut of 5 and a cut of 5, it gives me negative 2. I can't have a width of negative 2. And I can't have volume that goes on forever and ever, because I can't have cuts of 7, because 11 minus 7 gets me what? 11, 4, negative 3. And if this was 7 and 7, that's negative 1, negative 8. That's the only reason your volume goes back up to being positive, because a negative times a negative is a positive. Janine wishes to construct a cylinder. Well, remember what a cylinder looks like? It's like a roll of toilet paper. She's going to close it at both ends. The figure below shows the graph of the cubic polynomial function used to model the volume of the cylinder. Well, gee, volume is three-dimensional, length times width times height. No kidding that it would be cubic then. If the cylinder is constructed using 150, and sorry people, that should be a square. 150 square centimeters of material, use the graph to answer the questions below. We're going to estimate values to the nearest half unit on the horizontal or x-axis and to the nearest 50 units on the vertical axis. All right, so what do we got here? What is the domain of the volume of the function? All right, the volume function. Well, the volume function is this whole thing right here. So it goes from negative infinity to infinity. However, if we want to only talk about the part that makes sense pertaining to Jean's little cylinder here, then that's going to be the part from 0 to, let's see, that's 6, 7, 8.5. It would be impossible to use numbers outside this range. It wouldn't, sorry, outside this domain. Got to use my right words there. It wouldn't make sense to have a radius of 10, because a radius of 10 is giving us back a negative volume. And that radius of 10 is based on the fact that we have 150 square centimeters of material. Now, we don't care, we don't know how she got this graph. We just want to analyze the picture. We'll do more creating the function, but right now we're still just trying to analyze the graph. What is the most volume that her cylinder can enclose? Well, that would be wherever the relative maxima is. And there it is, right here. So that looks to be 800. What radius would get that volume? Well, the radius is the x-axis. So at 5, it looks like she will get her most volume. The volume of a cylinder is pi r squared h, base area times height. Figure out the height of the cylinder. Well, right now we want you to take pause and realize that this is a two-dimensional graph where you know r means radius and v means volume. So when you go to do this problem, this is what your brain needs to think. They asked me to find the height, so therefore I have nothing to put into the variable h. They're asking me to where does it maximize? Well, I know maximize is this point right here, which looks to be 800 for the volume and 5 for the radius. So in for v, we'll go 800. Pi is a constant. And in for r, we'll go 5. Now all I have to do is solve this equation. 800 divided by pi times 25. Bring out my handy dandy calculator. 800 divided by, use pi, do not use 3.14. 10.185. So let's just call it height is 10.2.